Hello, everyone, and welcome to the second part of this three-part lesson on tests about the means. In the previous video, we talked about the hypothesis testing process and the one-sample t-test. We presented an example of a certain problem wherein we can uh, use the one-sample t-test, and we were able to go through the hypothesis testing process using that example. Now, in this second video, we will be presenting two other t-tests, the dependent or the paired t-test and the independent t-test. Let us begin with the dependent or the paired t-test. The purpose of this specific test is to compare the means between two related groups on the same continuous dependent variable to determine whether there is a statistically significant difference between these means. Now, whenever we are working with two different samples, um, we're usually interested in trying to determine whether or not the mean from one sample is significantly different from the mean of another sample. We can even extend this to determining whether one is greater than the other or one is less than the other. And of course, that would also determine what kind of test that we are going to use, whether it's a one-tailed or a two-tailed test. So the same idea applies in hypothesis testing to uh, these kinds of tests that we will cover in this part of the discussion. So let's just clarify first what we mean by two related groups. Whenever we would like to test the same group of people for an for a dependent continuous variable, meaning we would like to see whether or not there is a change in the random variable after a certain period of time, then we say that the sample that we are working with, because we're only working with a single sample, is considered to be a dependent sample. And an example of this is, for example, you're using two different types of thermometers, one digital and then one analog, and then you test both of the thermometers on the same person or the same set of individuals, then you're basically working with the same group of people. Therefore, it's the same sample. But you are collecting two different data or on the same variable from these individuals. Therefore, you would be able to come up with two different means. So same sample, but two different means, then that's a paired or a dependent t-test. Another example would be in making an intervention and then trying to test whether or not the intervention works for a specific group of individuals. You can test the the individuals for the variable of interest before the intervention, and we usually call it as a pre-test. And then after they go through that intervention, a similar test is provided for them, and then we measure them on the same variable of interest, and we compare their pre-test scores with the post-test scores and try to see whether or not there is a significant difference. So that's another kind of situation that would uh, make the dependent or paired t-test appropriate. So take note that the dependent variable here is continuous, which means that it must be measured on either the interval or the ratio level. All right. Some of the assumptions that we talked about for t-test also obviously apply to the dependent t-test, and we will be presenting these assumptions later in as we go through our example on the dependent t-test. So allow me to present to you the example that we will be working with. In order to test whether a new drug for individuals who suffer from high blood pressure affects their mental alertness, a random sample of 12 patients suffering from high blood pressure is selected from a large number of such patients who regularly visit an outpatient clinic. Tests of mental alertness are administered to these patients both before and after they receive the drug. Their scores are shown in the following table. So if we take a look at the scores, we notice that there are two different sets of data here. The data before the drug is administered and then the data after the drug is administered. Both of these data are scores of the same random variable, which is the mental alertness of the individuals involved in the study. Now, just to clarify, a larger score means better mental alertness. So a smaller score would mean a decrease in the mental alertness when we try to compare the before and after mental alertness score per individual. So for example, if we take a look at individual number one, who scored 10 before the drug was administered in the mental alertness test, and then 5 afterwards, we would be able to see that there is in fact a decrease. This is different for this other individual who scored 10 before the drug was administered and then a 12 after the drug was administered. Now, what we really want to answer is, or to determine, is whether or not the data provides us with enough evidence to support the claim that there is a decrease, there is a significant decrease in the mental alertness on average after receipt of the drug for the population of all such patients at this outpatient clinic. So we will assume that the mental alertness scores are normally distributed both before and after the treatment and in the population of all such patients at this outpatient clinic. We will also assume that the variances are equal in the populations, and we will apply an alpha value of 0.01. As we go through each of the steps in the process, we will consider the context of the problem. Let us begin with step number one. The null hypothesis would state that there should be no significant difference between the mental alertness scores, the mean score in the mental alertness of the individuals after the drug was administered and before the drug was administered. So we will be representing the mean after as mu sub A and then the mean before as mu sub B. On the other hand, the alternative hypothesis would contradict that claim. So it would say that there is, in fact, a significant decrease in the mean of the mental alertness scores of the individuals after in comparison to their mean before the administration of the drug. We also know, based on the statement of the problem, that we will set alpha to 0.01. Now, before we discuss how we can compute for the test statistic using the appropriate statistical calculator, let us consider first whether or not the dependency test is appropriate. So we go back to the intention of the dependency test and we ask ourselves, are we interested in comparing the means between two related groups on the same continuous dependent variable? Meaning, are we working with the same sample and then we measured the dependent variable two different times, and we're trying to compare the means in these two different times that the dependent variable was measured? And the answer to that question is yes. Therefore, the dependency test seems to be appropriate. Now let's take a look at the different conditions. So we will assume that the homogeneity of variance condition is satisfied. We also said that we will assume that normality is satisfied. In the context of randomization, we know that the sample is randomly selected. It is stated in the problem. And because the dependent variable, which is mental alertness score, is a ratio level data, then the measurement scale is also satisfied. So all of the assumptions of the dependency test is satisfied by the data. Now, this is the online calculator provided by the Social Science Statistics website that we will use to for the two dependent means. So what we're going to do here, if you notice, is that it has two spaces for two different treatments. We will just have to indicate the scores of the first treatment. And since we are comparing the after from with the before, we will input all of the scores after in treatment 1 and all of the scores in the data before in treatment number 2. We know that the significance level is 0.01, so we will choose that. And then the test that we are interested in is a one-field test because the alternative hypothesis is stated in such a way that the after mean is actually less than the before mean. And then we will press calculate so that the calculator would generate the results for us. Now, we're not going to do that. As you notice, I was not able to input the actual data on the online calculator, but I did that before the recording of this video. And this is the result. So the value of P is 1.24 and the calculated P value is 0.12116. So we proceed with the next part where we determine the rejection region. We take note of the alpha value and the type of test, which is one-tailed. Specifically, this is a left-tailed test because we're looking at the decrease in the value. So we say that we will reject the null hypothesis if the value of P is less than the alpha, since the significance level is 0.01. So P must be less than 0.01. Comparing the calculated p-value, which is 0.12, to the alpha value of 0.01, we are now able to make a decision about the null hypothesis. So since p is greater than 0.01, there is not enough evidence to reject the null hypothesis, and the result is not significant at alpha is equal to 0.01. Finally, we write a conclusion, and then we say that the mental alertness of the patients before. So notice that similar to what we did in the previous example, we also give the mean and the standard deviation. But this time, since we're working with two different data sets of the same individuals, then we will have two means and two standard deviations, and we state both of them. So the mental alertness of the patients before and after were compared using the dependent t-test at a 1% level of significance. Mental alertness did not significantly decrease after the drug was administered. So the t-distribution is used, and the degree of freedom is 11 because the sample size is 12. So that's 12 minus 1, that's 11. And this is equal to the test statistic of 1.24, and the p-value is 0.12. Right, so I think we are now ready to discuss the third test in this lesson, which is the independent t-test for the mean. Just to clarify how the independent t-test is different from the dependent t-test, this type of test is used when we actually have two different groups of individuals tested on the same random variable. So if we are interested in comparing the means of two independent groups, in order to determine whether there is a statistical evidence that the associated population means are significantly different, then the independent t-test is appropriate. Now take note that the two independent groups are determined by a dichotomous categorical variable. So for example, sex is an example of a dichotomous categorical variable. We say that a variable is categorical if its values are categories, and we say that it is dichotomous if there are two values only of the categorical variable. So since biological sex is either male or female, then that means that it is dichotomous. Another example would be smoking preference. A person may either be a smoker or a non-smoker. Pregnancy, a person may either be pregnant or not pregnant. And even grades can be considered to be a dichotomous categorical variable if it is defined as whether it is passing or failing. Okay, so let's take a look at an example of a problem or a context where we can use the independent t-test. 32 people were involved in an experiment to determine whether background noise, such as music, slamming of doors, people making coffee, affects short-term memory or recalling words. Half of the sample were randomly allocated to the noise condition and half to the no noise condition. So we start with a sample of 32. We divide the 32 into two groups. That makes the groups independent of each other. So take note, we're not just working with a single sample. We're now working with two different samples that are independent of each other. And that's what makes it that's what makes the independent t-test more appropriate than the dependent t-test. The participants in the noise condition tried to memorize a list of 20 words in 2 minutes while listening to a pre-recorded noise through earphones. On the other hand, those who are in the no noise condition or the no noise treatment are participants who wore earphones but heard no noise as they attempted to memorize the same words. Immediately after this, they were tested to see how many of the 20 words they recalled as part of the memory test. And the number of words recalled by each person in each condition were recorded and are now shown at the right. So we have 16 individuals in the without noise treatment, and then 16 individuals in the with noise treatment. Here's a question that you want to answer. At alpha equals 0.05, did those in the without noise group perform significantly better in the memory test than those with the with noise group? All right, so let's go through the hypothesis testing process, beginning with the null and the alternative hypothesis. So answering the question negatively, we are able to frame our null hypothesis, meaning there must be no significant difference between the two different means. So mean sub 1 must be equal to mean sub 2. The alternative hypothesis, of course, contradicts that again, but more specifically because the question is phrased to state that one group performed better than the other. More specifically, yung without noise group performed better than the with noise group, then we say that mean sub 1 is greater than mean sub 2. So the first group is the without noise group, meaning mean sub 1 is the mean of the without noise group, and the mean sub 2 is the mean of the with noise group. We have already set alpha to 0.05, and now we can proceed by testing the conditions and the appropriateness of the independent test. So we ask the question, are we interested in comparing the means of two unrelated groups on the same continuous dependent variable? The answer is yes. We have two different groups with noise and without noise, but these two groups are tested on the same variable, dependent variable, which is the score in the memory test. Are the conditions for using the independent t-test satisfied by the data? Let's take a look at each of them one at a time. Again, we shall assume that the variances of the two different groups are not significantly different. We shall also assume that both of the sample distributions are normally distributed. It would be easy to determine that the sample is randomly chosen. It's based on how the context is presented. And then we know that the measurement scale condition is satisfied because the memory test score, is a random variable in the ratio level. And finally, since the performance of one participant in the experiment does not affect the performance of another participant, then we say that the independence condition is also satisfied. So all of the conditions, well, at least for those that we can check, are satisfied, and we assume the other ones that we are not able to test, then we say that we can now use the independent t-test. So the online calculator for the independent t-test can be found in the same link that I have sent to you. And in this case, notice that there are two treatments again, but these treatments again are independent of each other. So we input the data on the first group here and the data for the second group here. And then we set the significance level to 0.01 and the type of test as one pair. So we can now choose to calculate the results of the t and the p-values. Once we do that, we should be able to find that the t-value is equal to 4.82 and the p-value is 0.000019. All right, so the rejection region is determined by the critical value or the test statistic. But since we're using the p-value method, we will refer to the value of alpha, which is 0.05, and try to see whether or not or how the calculated p-value compares with the value of alpha. So we will reject the null hypothesis if the p-value is less than 0.05. Now, since it happens that the p-value is in fact less than 0.05, we say that there is enough evidence to reject the null hypothesis and that the result is significant at alpha equals 0.05. Now we can write the conclusion for this hypothesis test. And we say that at alpha equals 0.05, those who did the memory test after memorizing words without background noise, statistic provided, were found to have performed significantly better than those who memorized the same words with the background noise. So notice that our sample size is 32, but our degree of freedom is 30. That's because we're working with two independent groups. So instead of n minus 1, we will subtract 2 from n to represent the two different groups of individuals that participated in the experiment. So the DF, or the degree of freedom, is 30. The test statistic is 4.82, and the p-value is less than 0.01. So we notice that since the p-value is a very small number, we don't need to actually state the actual value here. Usually, if the value is already less than 0.01, we just say that p is less than 0.01. And that's enough data to sort of support the conclusion. All right, so this ends the second video, the second part of the lesson on test about the means. I hope that you were able to understand the idea of when we find the dependent and the independent t-tests to be appropriate, and that the examples were helpful for you. Please continue with the next video on the analysis of variance.